Question 10. Kinematics of particles. A small ball is projected from a fixed point O, so as to hit a target T, which is at a horizontal distance of 9a from O and a height of 6a above O. The ball is projected with speed square root of 27 ag at an angle of theta to the horizontal. We put u equal to the square root of 27 ag, as this will simplify some of our equations. The ball is modelled as a particle moving freely under gravity, so the acceleration in the vertical direction will be minus g. We're asked to show tan squared theta minus 6 tan theta plus 5 equals 0. Let's assume that it reaches the point big T, is that t equals big T, and now we can write equations for the horizontal and vertical motion. The horizontal motion, travelling at a constant speed of u cos theta for big T seconds, it travels a distance of 9a. So 9a equals ut cos theta. We consider the vertical motion. We're going to use the Suvat formula, S equals ut plus a half at squared. And here, S, the displacement, will be 6a in the positive direction. The vertical velocity is initially u sine theta, is travelling for big T seconds, and the acceleration a is minus g, so we get minus a half gt squared. Rearrange the first equation to get an expression for t, and substituting this into the second equation, we get 6a equals 9a tan theta minus a half g times 81a squared over u squared cos squared theta. We substitute u squared equals 27ag into this equation, and now we're going to simplify. We'll multiply through by 2 to get rid of this half. We see that the 81 divided by 27 is 3, and we're going to divide through the whole equation by 3. So we're going to multiply by 2 and divide by 3. So here we get 4 equals 6 tan theta minus sec squared theta. We use sec squared theta equals tan squared plus 1. Rearranging this equation, we get tan squared theta minus 6 tan theta plus 5 equals 0 as required. We're told there are two possible angles where theta 1 is greater than theta 2. When we factorise this quadratic, we can see that we have tan theta 1 equal to 5 and tan theta 2 equal to 1 as the two solutions. We're told the particle is projected at the larger angle theta 1, so tan theta is 5, and we've got to show the time of flight is the square root of 78a divided by g. So as tan theta is 5, we can draw a small right-angled triangle here with a height 5, base 1. The hypotenuse will be root 26 by Pythagoras, and now we can read off the sine and cosine of theta as we require them. We consider the horizontal motion. 9a equals ut cos theta. So big T is 9a over u cos theta. We can substitute the values for u and substitute the value 1 over root 26 for cos theta. We get t equals the square root of, we've squared the 9a and put it inside the surd, so it's the square root of 81a squared, then times 26 over 27 ag. Simplifying this, we get t equals the square root of 78a over g as required. Finally, we're asked to find the speed of the particle immediately before it hits the target t. So the horizontal velocity will stay at u cos theta. We write v as the vertical velocity. So considering the vertical motion, using v squared equals u squared plus 2as, we have v squared equals u sine theta all squared, that's the initial velocity all squared, The displacement s is 6a, and the acceleration is minus g. So that gives us minus 12 ag. Here, as we're trying to find the magnitude of the total velocity, this total magnitude squared is going to be v squared plus u squared cos squared theta. So adding cos squared theta to both sides, we get u squared sine squared theta plus u squared cos squared theta minus 12 ag. These two here will sum to be u squared, as sine squared theta plus cos squared theta equals 1. So the right-hand side becomes u squared minus 12 ag. We substitute root 27 ag for u, and we get u squared as 27 ag minus the 12 ag gives us 15 ag. To work out the magnitude of the resultant velocity, we simply take the square root of this expression, so that the speed equals the square root of 15 ag.